The Extremely Large Telescope will be the largest optical and infrared telescope in the world, producing images 16 times sharper than those from the Hubble Space Telescope. It will make the most detailed studies of planets around other stars, the first galaxies in the universe, supermassive black holes, and the nature of the universe's dark sector. And we're going to learn more about it starting right now. Hello everyone, welcome back to Launchpad Astronomy. I'm Christian Reddy, your friendly neighborhood astronomer. This video is about the Extremely Large Telescope, or ELT. ELT's origins date back to the late 1990s, when the European Southern Observatory started to think about the next generation of telescopes. They just finished building their Very Large Telescope, or VLT. VLT consists of four 8-meter telescopes. By combining the light from all 4-unit telescopes, VLT can achieve a resolution equivalent to a single 130-meter telescope. This technique is called interferometry, and while it does achieve high resolution, it simply cannot collect as much light as a real telescope of that same aperture because there are far fewer reflecting surfaces. In the early 2000s, ESO looked into the Overwhelmingly Large Telescope, or OWL, a 100-meter telescope. The proposal carried a 1.5 billion euro price tag, but it only had somewhere between a 75 to 90% chance of success. Those are not good odds when spending that kind of money, so the project was resized down to 42 meters. A 42-meter telescope would have answered the question of life, the universe, and everything, but its overall price tag was only down to about 1.3 billion euro. In 2011, the telescope was resized again, this time by removing the outer ring of segmented hexagons. This brought the price tag under 1.1 billion euro, and all of the participating countries committed to the project. Another way to keep the costs under control is to make sure that the overall design is as compact as possible. This meant introducing a unique 5-mirror design which will fold up the light path. The primary mirror consists of 798 hexagonal segments. Each segment is about 1.4 meters across, but is only 50 millimeters thick. That makes the mirrors lightweight and easy to produce. The secondary mirror is convex-shaped. It's 4.2 meters in diameter and weighs 3.5 tons. It will be the largest secondary mirror ever employed on a telescope and the largest convex mirror ever produced. The mirror will be shaped and polished to a precision of 15 millionths of a millimeter. In order to achieve the sharpest, highest resolution images possible, ELT employs the most advanced adaptive optics system ever developed, making use of a fourth mirror that is 2.4 meters across, but only 2 millimeters thick. 8,000 magnetically levitated actuators will readjust the surface of this mirror up to 1,000 times per second to correct for any distortions in the incoming light introduced by Earth's atmosphere. Up to 8 high-powered lasers will create artificial guide stars for the adaptive optics system to build up a 3D map of the atmospheric turbulence between the telescope's mirror and the top of the sky. This system will provide an improvement of about 500 in ELT's resolution, allowing ELT to resolve images as sharply as the laws of physics allow. When ELT begins operations in 2024, it will be equipped with 2 state-of-the-art first light instruments. The high angular resolution monolithic optical and near-infrared integral field spectrograph, or HARMONY, is a spectrograph that's designed to be set up and calibrated very quickly, allowing ELT to achieve a kind of point-and-shoot capability so that if something interesting happens, they can stop what they're doing and swing over and take a look at an exploding star, gamma ray burst, or anything else going boom in the night. It will be able to probe high redshift galaxies racing away from us in the expanding universe. It will even have the ability to achieve one of ELT's highest priority scientific goals, to directly analyze the atmospheres of extrasolar planets in great detail. The Multi-Adaptive Optics Imaging Camera for Deep Observations, or MICADO, will be capable of diffraction-limited imaging at near-infrared wavelengths. The sensitivity of this camera will be comparable to the James Webb Space Telescope, but will have 6 times the resolution. It will image the center of the Milky Way galaxy in unprecedented detail, making ultra-sharp images of stars orbiting the supermassive black hole lurking in our galaxy's core. Even though ELT is designed to be as compact as possible for its aperture, its dome is the largest constructed for a telescope, dwarfing every other observatory. The dome has to be aerodynamic to keep a uniform wind flow over the telescope. The ventilation system keeps the wind flowing over the telescope smooth, automatically opening and closing to ensure a continuous laminar airflow over the mirrors. ELT will be located at Cerro Aramazonas in Chile. This site was chosen in part for its cool, dark, and dry skies, but also because of its proximity to the Paranal Observatory, which is home to the VLT. This allows the ELT to make use of existing infrastructure such as roads, electricity, and so forth. First light is expected in 2024. At that time, ELT will not just be the pinnacle of ground-based astronomy, but will also stand as a testament to our curiosity to understand the universe and our place in it. It will detect Earth-like planets from the wobbling motions of their stars. It will directly image larger exoplanets and even characterize their atmospheres. It will be able to detect water and organic molecules in protoplanetary disks around stars in the making. A major step forward in answering the question of are we alone and if life can exist beyond Earth. It will explore the first objects in the universe, looking back through time to study the first stars, the first galaxies, even the first black holes. It will help us to understand how galaxies, including our own Milky Way, form and evolve. It'll mark our deepest probe into the mystery of dark matter, as well as dark energy that accelerates the universe apart. ELT will give ESO much-deserved bragging rights as the largest eye on the sky, but it's hardly a zero-sum game. ELT represents an international collaboration, not just between countries and institutions, but also between the other next-generation telescopes such as the Giant Magellan Telescope, the 30-meter telescope, the James Webb Space Telescope, and many more. Now, if you'd like to learn more about the next generation of telescopes that are under development, I have some links to them which I'll provide for you both here on screen and in the description below. And if you'd like to join me on this journey through this amazing universe of ours, please make sure to subscribe and ring the notification bell so that you don't miss out on any new videos. Until we see you next time, I'm Christian Reddy, and keep watching the skies.